Hello, today we're going to explore how to graph sine and cosine functions, and more importantly, how their shapes change when we apply transformations. These graphs may look simple at first, but they are incredibly powerful. They describe patterns that repeat in both mathematics and the real world. So let's get started. By the end of this lesson, you should be able to identify the basic shapes of sine and cosine curves, understand how amplitude and period affect those shapes, and apply both horizontal and vertical shifts. You will also learn how to work with the general form of these functions and interpret what each parameter is doing to the graph. Before we begin graphing, let's take a moment to understand why this topic matters. Sine and cosine functions describe patterns that repeat over time. We see this in sound waves, heartbeats, seasonal temperature changes, and even electrical currents. So what we are learning today is not just about graphs. It's about understanding how patterns behave in the real world. Let's start with the sine function. The graph of y equals sine x has a smooth, repeating wave shape. It has a domain of all real numbers and a range from -1 to 1. It repeats every 2 pi, which we call the period. It passes through the origin and has odd symmetry, meaning it rotates around the origin. The zeros occur at integer multiples of pi. Now let's look at cosine. The graph of y equals cosine x is very similar in shape to sine, but it starts at 1 instead of 0. It also has a domain of real numbers, a range of -1 to 1, and a period of 2 pi. Cosine has even symmetry, meaning it mirrors across the y-axis. Its zeros occur at pi over 2 plus n pi. Sine and cosine are closely related. In fact, cosine can be thought of as a shifted version of sine. Specifically, cosine is equal to sine shifted to the left by pi over 2. This means both functions have the same shape. They are just offset horizontally. To graph sine and cosine efficiently, we use 5 key points to represent one full cycle. These points mark the start, the maximum, the midpoint, the minimum, and the end of the cycle. Once these 5 points are plotted, we can connect them smoothly to form the graph. This method gives us a quick and accurate sketch. Now let's talk about amplitude. Amplitude tells us how tall the graph is, how far it moves above and below the midline. It is simply the absolute value of A. If the absolute value of A is greater than 1, the graph stretches vertically. If the absolute value of A is less than 1, the graph shrinks. And if A is negative, the graph reflects across the x-axis. In this example, we compare graphs with different amplitudes. Notice that only the height changes. The spacing of the graph and the location of the x-intercepts remain the same. So amplitude affects only the vertical scale, not the period or horizontal placement. Next is the period. The period tells us how long it takes for one full cycle of the graph. The formula is period is equal to 2 pi over the absolute value of b. If b is larger, the graph compresses horizontally, and if b is smaller, the graph stretches. So b controls how wide or narrow each cycle is. Here we compare two cosine functions with different values of b. One graph completes multiple cycles quickly, while the other graph stretches out slowly. This shows how changing b affects the horizontal spacing of the graph. If the coefficient a is negative, the graph reflects across the x-axis. This means peaks become valleys and valleys become peaks. However, the amplitude and period remain unchanged. Only the direction of the graph changes. At this point, you should be able to identify amplitude and period just by looking at an equation. You should also understand how changes in a and b affect the graph. This foundation is important before we move on to more complex transformations. Now we bring everything together. Every sine and cosine function can be written in the form y is equal to d plus a sine of b of x, b times x minus c, or y is equal to d plus a cosine of bx minus c. Each parameter has a specific role. A controls the amplitude, B controls the period, C controls the horizontal shift, and D controls the vertical shift. Understanding these four values allow us to graph any function. Now let's slow down and focus on phase shift. This is one of the most important concepts. The phase shift tells us where the graph begins. We find it by solving bx minus c is equal to 0. This gives us x is equal to c over b. This value is the starting point of the graph. It is important to understand that we are not guessing the shift, we are solving for it. If c is positive, the graph shifts to the right. If c is negative, the graph shifts to the left. To make this clear, always factor first. A times sine of bx minus c is equal to a times sine of b times c minus c over b. This makes the shift easy to identify and avoid sign mistakes. Once we find the starting point, we use the period to build one full cycle and divide it into 4 equal parts. Let's do an example. Let's walk through this example carefully. We are given y is equal to 4 sine of 2x minus pi over 2. First, identify the parameters. A is equal to 4, b is equal to 2, and c is equal to pi over 2. Next, find the amplitude. Absolute value of a is equal to 4. Now find the period. 2 pi over the absolute value of b is equal to 2 pi over 2, which is equal to pi. Now find the phase shift. C over b is equal to pi over 2 divided by 2, which is equal to pi over 4. So the graph starts at x is equal to pi over 4. Now we build one full cycle from pi over 4 to 5 pi over 4. Divide this interval into 4 equal parts and apply the sign pattern. Start at 0, go up, back up to 0, go down, and return to 0. Then scale the values by 4. This gives us the 5 key points needed to graph the function. Now consider the value d. This shifts the graph up or down. Instead of oscillating around 0, the graph oscillates around the line y is equal to d, which we call the midline. The amplitude and period do not change, only the vertical position changes. In this example, all transformations are present. We begin by factoring to identify the phase shift. Then we determine the amplitude, period, horizontal shift, and vertical shift. Finally, we plot key points relative to the new midline and sketch the graph. Now we reverse the process. Given a graph, we identify the midline, amplitude, period, and starting point. Then we use that information to build the equation. This allows us to move between graphs and equations. At this stage, you should be able to identify all 4 parameters, a, b, c, and d, and explain how each one affects the graph. This is the key skill for this section. Now let's apply everything to a real-world situation. We are modeling temperature using a cosine function. We are given a maximum of 97 and a minimum of 57. First, find the amplitude. 97 minus 57 divided by 2 is equal to 20. Next, find the midline. 97 plus 57 divided by 2 is equal to 77. Now find the period. Since the cycle is 12 months, 12 is equal to 2 pi over 2, which means, 12 is equal to 2 pi over b, which means that b is equal to pi over 6. Finally, shift the graph so the maximum occurs at month 7. This gives t of t is equal to 77 plus 20 cosine of pi over 6 times 7 t minus 7, close parentheses, close parentheses. This model describes how temperature changes throughout the year. To graph any sine or cosine function, follow these steps. Identify parameters, find amplitude, find period, find phase shift, find the midline, plot 5 key points, then connect the curve. Now try this problem on your own. Work step by step and identify each parameter carefully. Finally, to summarize, sine and cosine graphs are controlled by 4 parameters, A, B, C, and D. These determine the height, width, horizontal shift, and vertical position of the graph. Once you understand these, you can graph any sine or cosine function. In the next section, we will explore tangent and other trigonometric functions, where the behavior becomes very different and even more interesting.